Once again, welcome back in this lecture series of pre-CIMPA, namely pre-CIMPA lecture series. So, in this lecture series today, today's speaker is Professor J Athreya, and I welcome you, sir, in this lecture series and also in Banaras Hindu University in online mode. Yeah, and yeah. So, Professor Athreya is actually at the University of Washington at present. He is a professor there, and he actually completed his PhD degree from University of Chicago, and then through several universities, he nowadays at present he is in Washington, University of Washington, and today he will give talk on what is modularized space, and as Krishnendu just discussed that he is very on news actually because of a very interesting investigation, and hope within his talk he may say something about that because it's well known to everybody. So now I request Professor Athreya to please start your talk. Yeah.
Thank you very much, Professor Tiwari. It's a great honor to be here. Actually, I have a family connection to Banaras Hindu University. My maternal grandfather, late Professor Narendranath Siddhanta, he was originally from Guwahati, or Jorhat in Assam. He did his PhD from Banaras Hindu University in the 1940s, actually.
Oh,
Before he went on to found the chemistry department at Guwahati University.
oh,
My grandfather studied there, and so I would very much like to come and visit BHU in person someday and see where my grandfather studied.
you are
So it's
welcome.
nice
You
to
are.
be here. Thank you. It's nice to be here virtually. So let me start as as uh, as Professor Tiwari said, I'm going to try and tell you about what is a moduli space. So, like many things in mathematics, it's it's best instead of we starting with the definition, we're going to try and start with some examples. So a moduli space is going to be a space for me. It's going to be a space of different ways of putting geometry on a fixed topological object. But that sounds a little bit fancy, so let me start by starting with something very concrete. By the way, I should also say that you should feel free to ask questions at any time during the talk. If I'm saying something that doesn't make sense, or that is confusing, or if you just need a clarification, please ask a question. Either you can just unmute yourself and ask, or I will try and keep an eye on the chat messages as well. So let me start with a very informal, not really a definition, but just kind of um, a impression. So for me, a moduli space is kind of a space of shapes up to some idea of equivalence. And you've heard some things about some hyperbolic geometry and some flat geometry in warm-up talks. Today we're going to explore some things with just some flat geometry. So the spaces we're going to consider are spaces of sort of geometric surfaces, and I'll explain what geometric means, up to isometry. That's what we're going to explore in these two talks today and tomorrow. Today we're going to start with kind of a warm-up example. We're going to consider the space of triangles, just Euclidean triangles, up to similarity. And then we're going to also consider the space of flat tori, again, up to a notion of similarity. Up to similarity, here again, meaning sort of isometry and then scaling. But again, if I'm saying these without drawing pictures, they don't really make much sense. So I'm going to start to draw a lot of pictures now and try and explain what the space of triangles looks like and then what the space of tori looks like. So let's start with the space of triangles. So this is something we actually all kind of learn about maybe in high school or even before that, right? What do I need to have a triangle? So we say that, we go back to maybe elementary school, two Euclidean triangles are similar if you can rotate and scale one into the other. And of course, it's a classical theorem equivalently, right? What are the numbers that characterize similarity classes? Equivalently, the two triangles have the same set of angles. Triangles have the same set of angles. And so for instance, if I took this guy and this guy, these are similar triangles. I'll just use this to be similar. But maybe, this guy and this guy are not similar triangles, right? They very obviously have different angles. Another example of two things that may be similar is if I have this guy, these are supposed to be equilateral. These guys are similar as well, right? So I could how I draw it in the plane doesn't really matter. Rotating and scaling doesn't make a difference. Okay. So the question is now, how can we think of or picture the collection of all similarity classes of triangles? Okay, there's one very easy answer. I could think of this as the set of sort of theta 1, theta 2, theta 3 sitting in the positive cone in R3. I could say, let's take, all of these guys I want positive angles, and I want theta 1 plus theta 2 plus theta 3 is equal to, not 2 pi, but pi, right? That's, this is just considering the set of angles, except there's a little bit of a trick here, which is I don't actually care about this as ordered. So what I really want to do is I want to take this thing and I want to quotient out by, I can change the order of the angles. But of course, I could kind of draw a picture of this, right? I can draw a picture of this. Maybe this is the theta 1 axis, theta 3 axis, the theta 2 axis. And this would be, so maybe the points pi, pi, pi. It's this kind of triangle here, but it's the triangle quotiented out by the action of I'm allowed to permute the angles. So it's really, maybe I just want to think of sort of one piece of this, right? So, this is one approach. I'm going to describe to you kind of a different approach based on lengths of sides, looking at sides. So but again, you can kind of see there's maybe, you can kind of see in here already this idea that the space of triangles is itself a triangle. Even if we wanted to sort of quotient out and say, oh, we only care about ones where, let's say, theta 1 is bigger than theta 2 is bigger than theta 3, that would be a triangular piece of this triangle. But let's make this a little bit more concrete. Another version, another picture. Completely equivalent, but we're going to use something different, is we're going to say by scaling, assume the longest side has length 1. Let's label the next longest side as having length x, and label the shortest side as having length y. So we have, i.e. we have 1 is bigger than or equal to x is bigger than or equal to y. 1 is the longest side. We've scaled our triangle so that the side of the triangle has length 1. So maybe I'll draw you a little picture here. Maybe we had something like, B, let's see, maybe yellow, this thing, and this green. Maybe this was, A, and this was maybe some B, and this was some C. We could scale it and get a triangle, a similar triangle, where the long side now has length 1, maybe, and now we've scaled this guy, and sorry, that should be blue. And so now this I'm going to call this the second longest side x and the short side y. Okay. And so we have 1 less than or equal to x less than or equal to y. But of course, we also have, what's the other fact we know about the relationship between x, y, and 1? What kind of inequality could we use? What do we know about x, y, and 1? Maybe for one of the students in the audience, I can say, if 1 is the longest side of the triangle, and the other 2 sides are length x and y respectively, we have 1 bigger than or equal to, bigger than or equal to x is bigger than or equal to y. What else do we know about x, y, and 1? Is there some other inequality we know? Don't worry, there will be no penalty if you're wrong. But you could add something to the messages, or you can unmute yourself and say something. What's kind of the most obvious thing we can say about x, y, and 1? Ranadip, say it again.
Yes, it's x plus y is greater than 1.
That's right. Right? We know that x plus y is greater than 1, right? If this is a non-degenerate triangle. So excellent. So we have here x plus y is greater than 1. Okay. So now we actually have a really nice picture of our space of triangles. So I'm going to draw our space of triangles. Here's maybe the x coordinate, here's the y coordinate. We know that x has to be bigger than, so we have, here is the line, maybe here is 1, here is 1. Here is the line, x plus y is equal to 1. So maybe I'll draw that line in, maybe in yellow here. This is the line x plus y equal, x plus y is equal to 1. And then we know we're also, here's the line, maybe y is equal to x. And we know that both x and y are also less than or equal to 1. So we have x and y are both less than or equal to 1. So maybe here's the line. This is the line x equals 1. And then we have maybe the line here, y equals 1. That's a slightly less relevant line. But the point is, this is now our space of triangles. Our space of triangles is whatever is inside this thing. X plus y is bigger than or equal to 1. X plus y is bigger than 1. I have y is bigger than or equal to x, and x is less than or equal to 1. So my space of triangles is this region that I've shaded in white here. So I can write this as, so my space of triangles is the space of x, y, I have 1 bigger than or equal to x is bigger than or equal to y, and I have x plus y is bigger than 1. So it includes the right order, and it does not include this kind of bottom left. And notice there's a couple of things here. So I'll come back. I'll mention this in a second. Again, because this is going to be something important when we consider the space of tori. Actually, there's an identification between the triangles that are on the blue line. So the blue line these are isosceles triangles with the third side. Yeah, these are just isosceles triangles here, right? And I should just say this actually, with third side shorter than the first two. And this green one is isosceles triangles, because you have y equals x here, with the third side longer than the first two. So both of these are different kinds of isosceles triangles. The blue line and the green line are both isosceles triangles, but they're not the same kind of isosceles triangles, right? One is third side is kind of longer, and the one is the third side is shorter. You can think about what that means from an angle point of view as well. So again, each point in the shaded region represents some kind of triangle. So for example, there's a triangle that I like. So here are some triangles we can draw. So maybe here is the point. This is the point 1, 1 here. So that point corresponds exactly to the equilateral triangle, all of whose sides have 1, right? So that's the equilateral triangle 1, 1, 1. And that's, of course, that's a very special point. That's a very, very symmetric point. In some sense, it's the most symmetric kind of triangle. This guy, remember, is now this kind of this would be a degenerate triangle. This whole line is really degenerate triangles. But we could find some other interesting triangles here. For instance, if we take the triangle, what kind of a triangle is this one, for instance? Let me just take the point x equals 3/5. So maybe I'll draw in let's see, custom color, maybe this light orange. Maybe this point here, x is, let's say, 4/5, and y is, let's say, 3/5. So I have this point, which is maybe I'll just draw an arrow to it. That's the point 3/5, 4/5. What kind of a triangle is that? The one which has it's 3/5, 4/5, and then the third side has length 1. So any particular guesses on what kind of triangle that looks like? Three-fifths, 4/5 corresponds to what kind of triangle? Can somebody tell me what or at least what one angle of this triangle is? Beautiful. It's a right triangle. Thank you, Dr. Chauhan. Sorry. So I know these questions might seem basic, but the point is that they're going to help us when we think about the space of tori or the space of higher genus surfaces, which we'll look at tomorrow. Building our intuition with these simple surfaces, these simple examples, is really important. So you're exactly right. This is a right triangle. This is a 3/5, 4/5, 1, which is of course similar to the very famous classical 3-4-5 right triangle. Right? This is 3-4-5 right triangle, which is a really important and beautiful triangle. Okay, So let's try and see, in general, can we understand what this, so in this picture, let me go back to, so in this picture, can we see, sorry, not can we say, can we see some important families of triangles, important families of triangles. So again, let me redraw the picture, just keeping an eye now. I'll just draw one piece of it here, right? So this is, sorry, this is not the best picture to draw. So we have y equals x, x plus y equals 1. This is the line. This is x equals 1. This is x plus y is equal to 1. And this is y equals x here. So this is the point 1 half, 1 half. This is the point 1, 1. Sorry, that's not the one. This is the point 1, 1 here. So we've seen some examples here. This corresponds to this equilateral triangle. We've seen that we use this, sorry, I'm just going to try and remind myself what color we used here. This line, which was in blue, these were isosceles triangles. So were these green lines. These green lines were also isosceles triangles. And they meet at this point, this equilateral triangle. This equilateral triangle is this very special point here. These are these two kinds of isosceles triangles. But for instance, where can we see? We said, oh, this family was of right triangles, but can we see this? Can we see right triangles? Let me see where right triangles are. And of course, we can. What has to be satisfied? If 1 is the longest side, what's the equation that has to be satisfied for a triangle in this coordinate system to be a right triangle? So we saw one example, this 3/5, 4/5 right triangle. But can we see what, in general, what these right triangles look like? What equation do x and y have to satisfy to obtain a right triangle? Maybe Dr. Chauhan, I can ask you again. Anybody?
So,
What?
so yeah,
Neeraj.
so are we want to construct a right angle triangle? So put the like perpendicular bisector from the half of to line joining
Even
1 1 and 0 0.
not quite. What I want to say is that each point in this triangle that I've drawn is a
Okay.
is a triangle, and I want to think of each point as a triangle, and it's the triangle with side lengths 1, x, and y, where 1 is the longest side. So as Professor Tiwari said, use Pythagoras. So if we use Pythagoras, if we want the triangle with side length 1, x, and y to be a right triangle, what equation do x and y have to satisfy? Right. So that's right. So Tejbir, so what's the equation that I should write for x and y? I should write that x squared plus y squared is equal to 1, right? Is that what you meant when you said intersection with unit circle? So exactly right. So here is the you know, there is maybe the, actually I'll just change the color here. I'll use maybe a light kind of orange. And this is the curve x squared plus y squared is equal to 1. And this corresponds to right triangles. So these are triangles where the angles, one of the angles is 90 degrees. And so in particular, for instance, this triangle is a isosceles right triangle. Can somebody tell me what triangle this is? This is the, if you have an isosceles right triangle, maybe I'll color this one kind of this light blue. I'll color it kind of light blue here. That particular triangle, what does that correspond to? So that is, I have x is equal to y and x squared plus y squared is equal to 1. So what kind of triangle is that? That's exactly this 1 over square root of 2, 1 over square root of 2, 1 is the triangle. So it's an isosceles right triangle, right? And then the 3/5, 4/5 triangle is on here. And then what's even more fun is you can kind of go back and you can say, well, these guys, that set here, this is the set of, these are obtuse triangles because they have an angle bigger than 90 degrees. And then these are going to be the, maybe I'll color this one in using some squiggles. This set covered in squiggles, these are the set of acute triangles. Right? All the angles are less than or equal to 90 degrees. So what we can see is this is kind of a map of the space of all triangles. This triangle itself is a map of the space of all triangles. And by looking inside of this, we can read off different things about the geometry of the triangles. So the idea is, the key idea is where we are in the space of triangles tells you something, tells us something about the geometry of our individual triangle. Individual triangle. Right? So being on this circle says you're a right triangle. Being on either of these edge lines says you're an isosceles triangle. Being below, sort of below and to the left of the circle says you're an obtuse triangle. Being above and to the right says you're an acute triangle. So where you are in this moduli space tells you something about the geometry of our individual triangle. Okay, so now let's move on to a slightly more sophisticated example. By the way, maybe I should pause for a second and ask, are there questions about the space of triangles? Okay, and of course you can feel free to ask me questions tomorrow or send me an email and ask me questions. I know it's not always easy to think of a question just as you're listening to a talk. So let me now go on and talk about the next example, example 2, which is a little bit more sophisticated, which is the space of flat tori. Okay. So for instance, I think we've all probably seen this picture. We take a square, we identify opposite sides, and we get a torus, right? So we have, one curve, which is maybe this curve, and then we have the other curve going around, which is the curve, which is the second curve. If you want, we can use colors. We could say this is maybe the yellow curve, and that would become this guy here. And then we have maybe the green curve, and that would become this green curve here. Right? Yellow curve and the green curve. But of course, I didn't need to start with a square, right? So could start with any parallelogram and identify opposite sides. So for instance, you could try something maybe very long and skinny, right? So it could be very, very tall. Maybe this is my yellow side is the very, very tall side. And I have the green side is the green side is this very, very narrow side. And then this thing would look like something very different. It would look like this very long, skinny torus, where, going around the yellow was this very long guy, and going around the green was this very short guy, right? So, whatever I draw is, it really depends on the shape of the torus depends on the shape of the parallelogram. Okay. So how do we understand this space? Okay. So you could think of you could have kind of the way I explain this sometimes is a torus could look like a truck tire, or it could look like a bicycle tire, and those things are different. Or it could look like kind of a vada, something like that, or it could look like a jalebi. All of these, and they kind of we want to try and understand what are the shapes of all of these things which have one hole. Just like with triangles, we will consider these these tori up to rotation and scaling. And in fact, what we're really going to do is we're going to consider, whenever we say tori, we're just going to think of a parallelogram, right? It's a parallelogram with opposite sides glued to each other. So we're going to be allowed to rotate them. We're going to be allowed to spin them. We're going to be allowed to stretch them. So once again, just like with the triangle, what we're going to do is we're going to take it so that we're going to rotate and scale so that the shorter side has length 1 and is horizontal. Okay. So I have my parallelogram. The shorter side has length 1 and it's horizontal, and now the longer side maybe is looking something like that. Okay, so the longer side is it's some number. I mean, it's some kind of vector. I'm going to actually just think of this as some complex number, z, right? I have my horizontal side as 1, and then the second side is z. So I think of z as kind of being having absolute value bigger than 1. And the way I've drawn it, I kind of want to draw like this. I want to also think of this as being in the upper half plane. I want to think about the imaginary part of z as being positive. Otherwise, I could just flip the parallelogram. If I had a parallelogram that looked like that, this was 1 and this was my z, I could just flip it, and I would get one which has my z being positive, imaginary part of z being positive. So I think the z is now not a real number, but a complex number. and I have z, the absolute value of z is being bigger than 1. Okay, and so I have, my picture is that here is C is actually, what I'm actually drawing is the upper half plane, and I have everything outside of the unit circle. This is absolute value of z is equal to 1. So everything outside here so far seems to represent a torus. But what I want to do is I want to make an observation that I actually have, there's some more quotienting out that I want to do, not just scaling and rotation. There's a little bit more that I want to say. I want to say that, for instance, here are two tori that I want to think of as being the same. So let me draw with some colors now. So maybe I'll draw a square torus, maybe with some yellow and some blue. And then I want to draw something that looks kind of similar, but is not, I'm going to claim it's actually going to be the same torus. And what I'm going to do is I'm going to, oh, sorry, that should have been a blue. What I'm going to do is I'm going to say, oh, let me cut this along this green. Then I can reassemble this by doing the identifications. And I will get now something that looks very, very similar. I will get blue on top, blue on the bottom. I've cut on this and I've reassembled. I'll have green on either side. And I will have this kind of yellow line going across the diagonal. But really, it's the same square torus, right? It's just by cutting and regluing. What I've done, all I've done is I kind of took, in this picture, I just said, if this was my z, so this corresponds to z equals 1, this corresponds to z equals 1 plus I, because this blue guy is just, excuse me. This corresponds to z equals I, and then that's z equals 1 plus I, and these are really the same. So my point is that sort of z is equivalent to z plus 1, is equivalent to z plus 2. All of these are equivalent. So really, our z is only well-defined up to shifting by 1. So remember, we had earlier said that we had this upper half plane. We had minus 1 and 1. We had everything. We had all the possible z's outside of here. So this is this upper half plane. But really, we can always move our z by steps of size 1. And so what we're going to do is we're going to make a very specific choice. We can take the real part of z and insist that it has absolute value less than or equal to 1/2. So what we're going to do is we're going to draw these lines, and really our entire universe is going to be this subset of the upper half plane, which consists of the set of z's where absolute value, so this is the set of z's in the upper half plane, i.e. the imaginary part of z is positive. I want absolute value of z to be bigger than 1, and the absolute value of real part of z to be less than or equal to 1/2. That is my space. This is my space of flat tori. Okay. So just like with the space of triangles, we can, so just like the triangle case, where you are tells you something about your geometry. So let's go back to this picture and let's really try and understand what's going on with some very particular examples. So maybe -1, 1, here's maybe 0, here's -0.5, here's a half. So this is our space of tori. Interestingly, as you may have heard from Professor Gangopadhyay, this space is actually, again, this is a triangle, but it's now a hyperbolic triangle. So it's a triangle that has hyperbolic geometry to it. So the space of tori is a hyperbolic triangle. We'll come back to that in tomorrow's lecture. But let me label a few curves here, which I find kind of interesting. So let me just take, this is the axis. So this is the real part of z is equal to 0. Let's also label this bottom part, which is the, let's label this in kind of blue. This is the part where absolute value of z is equal to 1. So I actually want absolute value of z here in this inequality to be greater than or equal to 1. So there you have absolute value of z is equal to 1. And I want to try and show you what some different and interesting tori are on this. And then here, I'll draw you one more interesting kind of curve here, which is a yellow, just a flat line. That one is the imaginary part of z is equal to 1. So all of these are kind of interesting, and I want to try and explain to you what these different tori at various points look like. And that will be where we'll stop for today before we talk next time about higher genus surfaces and their moduli spaces. Okay. So, so for instance, this torus right here, the one which is on all three, yellow, blue, and green, this guy right here, let me actually color this green since it's that one right there, that's exactly corresponds, that's z equals, that's the point z is equal to I. So that's this torus I1, that's the original square torus. It's called a square torus. And then as we go up this line, we're going to get these longer and thinner rectangles, right? So as z gets bigger and bigger, maybe this is 1, and I don't know, this is maybe, I'll call this is the point e to the ti. That'll be the torus 1 e to the t. So it's much longer and much thinner, right? Its aspect ratio is getting the modulus of the triangle of the rectangle is getting very, very big. So as I go up, it's getting more and more distorted, right? The long side is getting much, much longer than the short side. This one is extremely interesting, and this is a really excellent exercise to work out, is that this torus here, sorry, let me color it in blue, is actually the same as this torus here. This corresponds to the point, this z is equal to e to the, well, this is, maybe this one is, z is equal to e to the I pi over 3. That's 1/2 plus square root of 3 over 2i. This is equal to z equals e to the, oh, I guess this should be 2i pi over 3. So this is equal to negative 1/2 plus square root of 3 over 2i. But both of these actually correspond to a rhombic torus or a hexagonal torus, which is very pretty. It's the one that has angle here. The angle here is pi over 3. The angle between the horizontal and that z. And so why do we also sometimes call it the hexagonal torus? It's because these, if you have 3 of these rhombi, oops, sorry, that would make up this nice hexagon here. Right? So if you have three of these rhombi, it would make up a hexagon. And you could also think of this torus as coming to you by identifying opposite sides of this hexagon. Right? That's also sometimes called the hexagonal torus. So once again, we see the kind of can absolute value of z equals 1? Absolutely, yes. Thank you. So we do allow absolute value of z equals 1. That's certainly something that we allow. And in fact, this whole blue curve is this where absolute value of z equals 1, and that corresponds in some sense to some kinds of isosceles tori in some sense. These are tori which have 2 shortest curves of exactly the same length. But again, you can see that the kind of edges of the space have very symmetric, very special points, right? So this point, this is kind of very symmetric. It has kind of order 4 symmetry. And this guy is also very symmetric. It has kind of order 6 symmetry or order 3 symmetry, depending on how you want to classify it. And this, again, is very similar to the space of triangles, where we had our endpoints or kind of edges or corners were very symmetric ones, right? We had the equilateral triangle, or we had these isosceles triangles on the edge. And finally, this yellow line corresponds to what are called kind of sheared tori. But once we get to these two edges are actually the same torus. So in fact, I should actually maybe draw this thing here, is this edge here, where z is equal to -1/2, is the same thing as this edge where the middle part of z is equal to 1/2, right? Because I can just add 1 to z. So these guys are actually the same. So in fact, this space of tori, you actually need to fold and identify these edges, and you get this beautiful picture of what's called a moduli space. So I'm at my time because I want to leave some time for questions. And next time, what I want to talk about is I want to talk about how this picture generalizes to what are called higher genus surfaces, how we can talk about what's called the moduli spaces of higher genus surfaces. And we can talk about both the flat and hyperbolic geometry of surfaces when we talk about these moduli spaces. It's going to be a little bit more difficult to draw pictures because the spaces of surfaces are now going to be much bigger dimensional. They won't be 2 real dimensions anymore. They'll be much higher dimensional, but I will still try and draw many pictures of the surfaces themselves. And so that will be the goal for tomorrow's lecture, which, as you'll hear from Professor Tiwari, will, due to some scheduling reasons, we'll actually have to start it at 5 o'clock instead of 3 o'clock. So, but I think this is a good place for me to stop and open it up for questions.
Any questions or comments? Any participant, any type of question, even if you want, you please ask, feel free to ask.
So I've tried to just recap the main point in the chat as well. So the main point is that we can package all possible shapes into a space. That space is the moduli space. Where we are in that moduli space tells us something about our original shape. So you've seen that hopefully for triangles and for tori. And thank you for the kind words. This is exactly, I really want to get people to say, here is what a moduli space is, knowing just some basic elementary geometry.
Yeah. So I think if there is no question, let us thank Professor J Athreya for today. And yeah, I'll see you tomorrow also for the second talk. So thank you very much.
Wonderful. Thank you. Bye-bye.
Bye-bye.